in my education. And that grow with me in the field of electronics and communication, and then that leads me to do a PhD in embedded systems, how to make it as a distributed system, and how to use like tools to work or to deal with the complexity that we see in the embedded system devices. So I moved from a very low level to up to a very high level, which you called using UML, something like SysML, to make languages and tools in order to design a distributed embedded system that somehow can work. And when I see the work Victor is doing with ROS2 and tooling to get the system to work with ROS and come back to the hardware, so I could see this methodologies that we built as a series back in the days now become to real. So I moved to University of Southern Denmark 4 years ago. That's because of the work for drones. And here I started putting ideas and then that becomes projects. One called Drones for Energy, one Drones for Safety, and another one is called Aerial Core. And I'm coordinating the first two. So when I moved to SDU like 5 years ago, I wasn't interested to see how they do energy inspection. So it happened that that they do it in this way. Like I have an inspector who's in a helicopter, and his daily job is mainly to make a check, to make an inspection of these high voltage lines. So you can see him. He's try to move his tools from the helicopter to the power line, and then he had a stick here to make his body equivalent to the 400 kilovolt. So he kind of wearing a Faraday cage around his body, and then he's using his hands and eyes to look for defects. And his daily job is to go back and forth to look for these defects. And yeah, and that also comes to other countries. Like the previous one was in the United States, this one is in Asia. And it's like kind of a common job. Yeah, these workers, they do it. So the first thought is like, okay, why we cannot just use drones, and instead of sending humans online and then make them do a tedious work. And then that is the first project idea came is to mainly build drones and let these drones fly around the power lines. But as we all know, the drones can fly for a short time, like 20 minutes. And then our part is to use a magnetic field to recharge the drones. So if you can build a drone that can land on the power line, harvest the energy, and then they can fly again, so we can do a job. And here we team up with Fraunhofer IMS in Germany to build a harvesting mechanism that could be attached to a drone and also still to be a lightweight, so if they can recharge the battery. To make it smart, we connect to this cloud services, and this way the drone knows where to go and when to go, and when it collects data, it sends back to the cloud. And in order to speed up this process, so we also run AI algorithm on board, so they detect these defects, and we fly these drones in a swarm. So we can, yeah, we can cover all of the 4 angles in the power lines, and then we let these drones communicate. So we use LoRaWAN, like a low power, long range wireless area network to send the coordination data between the drones so they can fly along the lines. So we can combine in this project swarm system, energy harvesting, and AI in the project. And that was funded nationally in Denmark, and they give us a budget of around 3 million euro back in the days. So we started building up these ideas, and then we started building drones. We were quite new in this area, so we built kind of basic drones. So a drone flies, in this case, it uses a BX4 flight controller and a Raspberry Pi with a pair of lidars to detect the line. And each time the drone sees the line, it ascends until it reaches the power line. So we use a PID controller to track and keep the drone in aligned with the cable, and then in this case it leaves a sensor on the power line, so it can measure the current passing through and then send some data back to the ground station. If you are interested in this work, you can, of course, read it. We put it all of our data open source, so you can check. This article was published in ICRA. It's a well-known conference in robotics. After we made the drone quite advanced, yeah. So in this case, we built a custom drone. So the full drone that you see is just this is built from scratch here. We added on the top the energy harvester, and also we used an NVIDIA card, because now we need to run the AI on board, and we see the Raspberry Pi cannot do much rather than for running a very lightweight control algorithm to track a line. And of course, plus we used ROS and ROS to communicate with the flight controller. Yeah, so in this case, we moved to NVIDIA. We run the AI, so we used YOLO. It was trained to detect the defects, and the drone using the LiDARs to follow the line. So now the drone is doing this autonomously. It looked for defects, sorry. Sometimes the video just stopped after 1 minute. So when it finishes the trip, it goes to the center of the line, and then it does the recharge landing. So in that case, the drone is grasping on the line and using the energy harvester, which here is a split core current transformer. I just stay here for a second. So this unit weighs around 1 kilogram, and it can charge the drone battery, which in our case is 10 amp hour, within 3 hours, 2 hours and 40 minutes. So expect here 800 amp to pass through the line that represent the primary current, and then the drone is harvesting energy. And then the drone flies 15-20 minutes afterwards. So we still have some optimization to be done. So we could save in the NVIDIA card a little and make the drone lighter, and try to incorporate more activities together to make it better. And that's what we actually aim for the next or the current work. Beside this work, we also test again is electromagnetic interference. So we built small drones covered by a Faraday cage, and then we touch it here 150 kilovolt lifeline, and then we thought, okay, all are good, so we can do it. We tried with the 400 kilovolt, that is the highest in our region here in Fin. But yeah, when we were doing this, the drone just crashed. That was too much electric field passing through the drone. So we understood what went wrong, and then we protected better. And then you can see the drone was working under the arcs, the electric arcs, and they touched the line without issues. So we now can touch high voltage line with our drones, and yeah, come back safe. So those ideas brought us to a next level, which is what we can do more in terms of an inspection. We see the power lines. They call that parallel infrastructure. So you have these cables moving in parallel with railways, with highways, but also we discover also with bridges. So it happened in 2018. In Italy, there was a sad accident in Genova. The bridge collapsed. And when we look to the data, we can see actually 70% of bridges in Europe are within 3-kilometer distance from power lines. So if I could see a futuristic drones that they can charge and then go to the bridge, make an inspection, and come back. So that is a scenario here in this project called Drones for Safety. And that is a new project that started in June 2020. And we aim to do the same, to inspect bridges and apply the same for railways. So the drone can inspect railways similar as it does with power lines. In the meantime, it also inspects bridges. So it's an EU project. So we have many international partners in 5 EU countries. Yeah, so we aim to build autonomous self-recharging collaborative drone system to inspect transport infrastructure. Yeah, and it has a budget of 3.7 million euro. We want to make it better. So we see now that the challenge, we would like to be smaller, we want to fly longer, and we would like to do many operations on board. So one of the advantages that an FPGA or a hardware accelerator give is mainly the reconfigurability part. So I could imagine the drone could be running one task, every task at a single time. So inspection, maybe later to do control to track a line, maybe later to send data to the cloud and so on. So we have several activities that they can run one after one. If we do it smart and the hardware, we could benefit a lot from the reconfigurability aspect and the hardware accelerators while also doing it in real time. So this is our current setup, is to have a classic drone approach, low-level flight controllers that keep the drone on air, communicate with the ground station. The classic approach that we in the past we used to do is to use a Raspberry Pi or an NVIDIA card to interact with sensors and then communicate with other nodes. And our current activities to replace these two is to use, we work mainly with Ultra 96, and hopefully in the future we will also work with KV 260. And yeah, so if you can run ROS2, we accelerate some nodes and well, we communicate and accelerate some activities as ROS nodes and the hardware that could be making accelerated sensor fusion data or running a DBU and then looking for defects and work around that. So we could have a high performance drone system at the end. We took the first step last year. So I had a master's student. He started trying to make an autonomous drone system to look for a marker on the ground. So he used Gazebo here with a YOLO neural network to detect this marker and to make a mission to land on the line in this marker. So he checked the functionality was working, and then he imported that to the Ultra 96 V2, and then use ROS with PX4 and make the same thing. The target is the box here, the unit here. So he's looking for a boat here, a picture of a boat, and then when it detects a picture, it lands. So I could see the performance of the drone is quite nice. It's very stable and it detects and land quite precisely. So I was quite impressed about the result here. So that is a published work called MB Drone, FPGA-based platform. It was just published in IEEE RAS SSRR conference. Yeah, and the system here mainly use BINC project, so to use the DPU to run the neural network, and then use ROS messages to publish and subscribe with some data, and then use a PID controller to steer the drone towards the target. And that was done using ROS and PX4. So on this side, you can see the hardware implementation. On this side, on the other side, you can see the software implementation in which we use Gazebo. Currently, we are working with, or heavily with Ultra 96. So thanks to Frederick and Nikolai for their activities to get that to work. So our current setup is like that. We have already Ubuntu 20.04 running on the CPU side of the Ultra 96. Having this Ubuntu, we can run ROS2 Foxy on top. That is also needed for the PX4, and then we use RTBS to communicate between the flight controller and the CPU. In between, we use Axibus to exchange data between sensors. sensor fusion algorithms here, and also Nikolai's testing with FIN neural network to detect objects. And then based on the results, this data is going up to the software, taking decision, and then we steer the drone right, left based on what we want to do. You can check out this. You can check out these activities and our GitHub group, the IISDU group. You can see how far we went. So for now, we have a working prototype. We can send commands back and forth. We can control a drone. We can also build custom IPs and also exchange data through XBus and PRAMs between the PS and PL sites. Yeah. We also interested in different types of sensors. So we surveyed all sensors on the market that we could detect overhead lines, and they have to be also in low cost and lightweight. So we tried with millimeter wave, high resolution time of flight cameras, stereo cameras, 8-segment LiDAR, and the classic cameras, and we make analysis to see how they react against the power line. And we could see here, stereo camera, they have a lot of noise. 8-segment LiDAR was quite okay. But we also were impressed about the millimeter wave that gives us really accurate results. So we have an idea now to fuse the millimeter wave data with other sensors in order to track the power lines. We put this sensor on the drone, and then we can also still see the millimeter is really tracking the power line, even from a very far away distance. If you are interested in this survey, it's also it's a published work, and also there is a big data set that shows all of this data. Okay, yeah, so our activities mainly around embedded systems for drones and system integration, building autonomous navigation and tracking system for cables, mitigating the electromagnetic interference, and harvest energy from the power line cables. These are the excellent guys behind the team. So Frederick Nebo is a PhD student, and Nikolai Mele is also a PhD student. Oscar is a drone engineer, and Nikolai, he was a former mechanical engineer. If you are interested, you can also get all of this from our website. You will get a page like that, and then there is a publication up here. You get all of the publications and also videos and what you have seen today. Yeah. So thank you for the attention.
All right, fantastic. Thank you so much, Emad Samuel. That was fantastic. Really exciting work you guys are doing, and looking forward to see those drones perching the power lines, recharging themselves, and ensuring that they are in good health. Good. So let's open it up for questions, I guess. Questions, folks. If not, I'll go first.
From a software libraries utilized in the different projects there, can I find that information in the papers? I'm just trying to identify where to go look, just so I can identify and perhaps prioritize in terms of what to optimize for similar projects, because I really connect with what it is being used for, right? One of them is the fact that it is for public safety and also the safety of the workers. So yeah, would be great to contribute in the way that I can, which is to identify the libraries that are useful and see how I can optimize them. Thanks.
Yeah. So in all of our publication, we really like the open source mentality. So we give back the knowledge to the society. So in all of the articles, we say how the drone is built, and also what kind of ROS packages we used and what kind of libraries we built. And the ones we built, we put them in our GitHub as free open source libraries to use.
Awesome, thanks.
You're welcome.
So just to get clarity on that, essentially, is the computational graph reproducible? Because I also saw you guys are using Gazebo for development purposes. So what you're saying is that you guys have pushed publicly the way to reproduce the simulation so that people can contribute?
Yes and no.
Okay. I mean, so sorry, that's kind of
yeah.
like the quickest way it comes to mind, to me at least, if you want to introspect the computational graph to identify the resources as it was being questioned. I guess that's the easiest way, right? To get it up to speed, to get it in Gazebo, and then to actually instrument things.
Yeah, we share the world that we built in Gazebo and also the nodes that we are running in Gazebo. In the paper, there is also the control algorithm which interacts between the ROS nodes in order to steer it towards the power line and what kind of weights we use in the PID controller. Maybe it could be we can think about to have it as an open simulator, so one could run the simulator and see what we see all the time, like power lines and the drones flying. So it could be an interesting approach to consider to have a full simulator as an open source with our environment as well.
I mean, for what concerns, and I'm sure like others might be interested as well, but for what concerns my interest, I definitely would be up for spending a few hours, guys, and try to reproduce your use case in simulation in Gazebo, and from there, of course, try to help with changes in the actual architecture and proposing changes here and there. But I think that's kind of like the baseline for trying to set some like common baseline, and we haven't yet reached that point in the working group, but eventually we will dive into case studies, right? And those case studies should be available for people to do things jointly. So, I mean, if you guys are up for it, it sounds like this would be a incredibly exciting case study, but we'll leave that to you.
Thank you for the advice.
More questions, folks?
And currently the perception is also accelerated apart from this neural network that you run on DPU. The camera, like how you detect the lines and also, is that also accelerated?
No, not yet. So for the moment, to follow the line, we use a pair of 8 segment solid state lidars. So this 8 segments tells you in which segment is the line is, and then we have a pair, so we can draw a line, and we use this few bits coming from the 2 lidars. With a classic PID controller running in a CPU, so that was okay to track a power line. Yeah, so our next is to do the acceleration using millimeter wave and also cameras, and that will become heavy for a classic CPU approach like a Raspberry Pi. And our target is to do that using HLS and the hardware side. So we could have a very low latency in the fused data, and thus we can speed up the flying speed of the drone. So for now we fly like 0.5 meter per second. That's really slow. That's because also the CPU that we are using is not really collaborative in our approach. But we have it in our pipeline to do in the hardware.
Okay, that will be interesting. Thank you.
On the on the millimeter wave, since you have an FPGA, are you going to tie that into the LVDS lines on the millimeter wave, or are you just using the sort of the SPI or UR output?
Yes, well, actually, Nikolai is also in the talk here. So he's building now he connected the millimeter wave with the FPGA through UART, and he kind of interpreting the UART messages. So it's moving through the hardware and then doing the acceleration on the hardware side. So this way we can save some time. And instead of going through the CPU, using the software libraries to get the data and then put it to the memory and pass it to the hardware. So we do that as a hardware to millimeter wave data processing.
And have you tested this in adverse conditions? Because I know that like probably only the millimeter wave will see this in, you know, like fog or whatever.
Yeah. So in this paper that I showed, the survey, it was we had the different tests. Well, usually it's a power line really give us really good result with this millimeter wave. But if you put the millimeter wave in a room, you will not really get any good data. That's because of the background reflections and it needs more post-processing in order to get a good data out of it. What we tested is was mainly during winter time, so it was kind of cloudy, snowy day. It's not really visible. It's not really a clear sky. The millimeter wave were around, I think, 20 meter far, and then up to 1 meter far from the power lines, and we could detect the lines. Yeah, so based on the data, the Texas Instrument is showing that it can go through the clouds and it can do good work when it comes towards different climate conditions.
So there's here another question from Joe in the chat. He asks, gazebo simulation is all digital. Are there plans to build a computer in the loop simulation to benchmark node execution on device? And by computer in the loop simulation, I presume you mean HITL, hardware in the loop, Joe? That's a common practice with UIVs. What do you think?
Yeah, so I guess there's the computer in the loop bit, which I was talking about, that would have sensor information basically dummied up for it with like a data creation node, say for IMUs or cameras. My question was more about, let's say we mock up interfaces to a simulation engine like Gazebo for those signals, then basically use the Ultra 96 in this case as a device for actually just running all of our processing nodes and then benchmarking there.
Yes, I mean, we follow this approach for with ROS and Raspberry Pi in general, that what we see in simulation, what we get in the Raspberry Pi. It's not a hardware in the loop simulation. That's because it's two separate things. Why we don't do that? That's because of the drone itself. The drone we see in the simulation flying nicely, it's not the same drone that we have it built flying outside. Different weights, different orientations, offsets here and there, cannot give us the same performance. We test the control algorithm are working fine. If they are good, then we put them in the drone, and then we do the tuning on the drone side in a real hardware. We don't really have plans to do hardware in the loop simulation. I think it will be really great if we can put the Ultra 96 as an accelerator platform with the communication with the Gazebo through UART or RTBS, and then we see, yeah, the drone is flying in Gazebo and the data is accelerated in the Ultra. Yeah,
thank you.
Awesome.
Yeah.
I think I might have missed part of that, Joe. Are you saying that you wanted to simulate basically Gazebo images and rendering off of a drone flying around the real world, or you're just wanting to pull in artificial IMU data, or because there is a way that we've used using motion capture with scaled down small city scale kind of type stuff on like a 1/50th scale to then basically use sort of like the hand of God plugin to basically drag around a UAV inside of Gazebo using the real world sensor info that's coming off of an actual miniaturized drone flying around in a motion capture setup to then refeed it visual image data from a world we have in Gazebo to then perform vision algorithms on, if that makes sense.
Yeah, I guess I'm thinking about maybe the inverse of that. I want a simulation engine to create synthetic sensor data for all of the onboard sensors. And then I would communicate that information to my my processing device, my SOM, and then just ideally the computing platform wouldn't know that it was being driven by simulation data. Like in the idealized world, it would run as close to the actual in-flight setup as possible.
Okay, so already in PX4, you can already do that if you plug in your FMU directly. There's an example of doing it, for instance, in PX4 where they put it over a Mavlink message, which you could very much replicate for what you're looking at. And IMU data is passed along from the simulation then directly over a serial connection to your connected end device. But also, if your device is already on a network, and if you wanted to use, for instance, like a ROS2 bridge to pass along the messages and standardize those messages, then as long as they're on the same network and your device is plugged in on that same network, you can have relatively low latency sensor data also be fed across through ROS2 to your end device, and then just create a synthesizing node on that end, which I've also done, but more specifically for the visual image processing side of it, and just some basic IMU to help out with some of our algorithms associated with some monocular SLAM.
Can you share a link for that, please, Benjamin?
Yeah, tell you what, I might shoot you. I'm sort of indisposed of being able to send stuff easily. Is my email address? Let me just shoot you my email address right here. If you want to shoot me an email, I can send you stuff on that.
Yeah, that sounds great. Thank you.
Okay. No worries. So there's my email address in chat, and if you want to shoot me an email, I'll send you along some stuff.
Cool. Thank you, Benjamin.
Thanks
Thank you, Joe. Thank you guys for the discussion. Yeah, I mean, for what concerns essentially, and I wasn't familiar with this computer in the loop term, Joe, but thank you for pointing it out. Frankly speaking, this is kind of like the setup I'm using for testing hardware acceleration, and the one that I'm constantly using. I'm using Gazebo as essentially the entity that's generating data out of the robot, and using ROS2 capabilities, and the computational graph gets down to my device in the local network, and I'm getting data directly from it without having to directly interface with hardware, which depending on the robot you're dealing with may become expensive, both time-wise and economically speaking as well. So definitely interesting that path, and also happy to see there's excitement in here. So we reached the top of the hour. Thank you everyone for meeting once more. Emad Samuel, thank you for sharing your use case. Very, very exciting. Thank you to you and to your colleagues for this fantastic work. We'll pay attention and look forward to hear and read more about it. And other than that, we'll meet soon. Essentially, next meeting is expected to happen next month, possibly. So yeah, stay tuned for more, and thank you for showing up, guys. Have a good one.
Yep. Thank you, everyone.
Ciao, ciao.
Great stuff. Thanks. Bye-bye.
Ciao.